Okay, good morning. This is geometry lesson 9.4, and this is on angles formed by secants and tangents inside and outside of a circle. And it isn't just actually angles, we're looking at the segments themselves, the secants and the tangents, and we're looking for measurements of those things. So this is a combination of line segments and angles, okay? Mostly segments, actually. So we will be able to determine the relationship between and the formulas. So relationship and formulas for chords, secants, tangents, and which are located inside and outside of a circle. So the relationship between formulas, chords, secants, and tangents located inside and outside of a circle. And so the idea is to solve for the measure of their lengths and their angles, okay? And so this video supports Delta Math Geometry Assignment 9.4, Properties of Secants and Tangents. Make sure that you upload those or the notes to these. Not only the notes, well, let me restate that. I want you to upload all the notes. Remember, I did a live portion of this, so make sure you have the live portion and then the rest of this. Now, I actually am going to tell you where we left off in just a few minutes, in fact, not in less than that. We'll tell you that, and you can fast forward this video if you want to that point. You must upload those notes to me by Wednesday, March 14th at 11:59 p.m. Okay. All right. So we actually went through example 1 here, and we also went through these theorems. So if you get to this slide, we're almost nearly done. There are a couple of examples at the end. So you might want to stop or pick it up here at this slide. So this is the third or the fourth slide where we were looking at the description of tangents and secant segments and the theorems. All right, so let's go back and let's start out with just a quick review. So I included this slide. This was actually from the previous video, 9.2. Was it? No, 9.3. So these were definitions of the parts of a circle and the segments involved. So we looked at the circle itself, the radius, which is this part from the center to the edge of the circle, and we looked at the diameter, which goes from one side of the circle to the other side through the center, and then we looked at the nature between the radius and the diameter. The radius is half the diameter, or diameter is twice the radius. Then we examined a chord. These are segments that are inside the circle and go from one side to another. So a radius is not included in the chords, but PR and PS, because they go from one side of the circle to the other, is included. We talked about the fact that the diameter is a special chord because it goes through the center of the circle. So it's both a diameter and a chord. And then this really takes us to where we are now. We are examining circles and the relationships with tangents, and a tangent is a line, or it could be a line segment, that only touches the circle at a point of tangency, and that point of tangency is at a perpendicular angle to the center of the circle. And you can draw the radius from the point of tangency to the center of the circle and form a 90-degree angle here. Secant is a line that passes through the circle. It would have to include the two edges of the circle, so one point on each side. And a lot of times secants don't go all the way through on both sides, but they do have an outside portion, an outside segment. So we'll be looking at that. All right. So let's get into the meat of things. The first theorem that we're looking at is the theorem on chords intersecting inside a circle. And basically, the rule is that if two chords intersect inside the circle, and so I've got a chord AB and a chord CD, and they intersect at E in the center of the circle, or inside the circle, then the product of each chord equals each other. So that would mean that from E to C, let's see, well, let's start with E to A. E to A here times E to B, this part here, is going to equal E to C, which is this part here, and E times E to D. Okay, so you can set up a little formula and you can solve for it. So we're going to do that in this circle here. I'm going to just create two chords. So let's see, I'm going to point Q over here and point R here, and I'm going to put point S up here, and down here I'm going to put point T. And I'm just going to draw using my straight edge, the straight edge of my protractor. I'm going to draw a couple of tangent lines. And I'm not really too worried about where these tangent lines are in relation to one another. And each time I've done this, it's been a little different. But here you've got the relationship, and what I'm going to do, I'm sorry, the intersection of the two. And I'm going to call the intersection R. So there's a point right here. It's called R. And I'm not really worried about scale, but I'm going to say that R to Q, that's from here to here, is 9 units. And R to P is X units, an unknown amount. And R to S is 3 units. And R to T here is 6 units. Okay? So we will set up a 2-column proof with this. And so I'm going to write a statement over here. And then I'm going to have the reason column over here. And so what I'm going to do is I'm going to take the theorem. The theorem is really our rationale and what makes this a proven thing. So I'm going to say that R to Q times R to P is going to equal R to S times R to T. So R to Q, that's one segment of the chord R, or QR, times R to P, and that's going to equal R to S times R to T. And again, the reason for that is the theorem on chords intersecting a circle. Now this is really the most important part of it, because if you didn't know this, you wouldn't know what to do. And some ancient philosopher figured that out and tested it, and his successors tested it, and they never could get it to do it incorrectly. It always did the same thing. If you took the two segments of a chord, multiplied them together, and that should equal the two segments of the intersecting chord multiplied together inside the circle. Okay, so now let's just substitute. So we're going to substitute. Well, this is number 1, by the way. And then number 2, substitute. So R to Q is 9 units. R to S is X units. I'm sorry, R to P is X units. I did this wrong. I showed it as an R as P. This is P. Okay. And R to S here is 3 units. And R to T is 6 units. So you're multiplying 9 times X, and that equals 3 times 6. So now after you substituted, you're going to simplify. So 9x equals 6 times 3 or 18. And then you're going to undo and isolate and solve for x. When you get x by itself, basically you are going to be isolating. So we're going to divide by 9 on both sides because 9, as we said, was multiplied to the x. So the opposite of that is division. We divide by 9. This is, let's see, I kind of smushed this together, but this is 4, 9, 3 and 4 put together. And then and this is basically division. Divide both sides. By 9. Okay. So you end up with x equals 18 divided by 9 is 2. Okay. So there you have it. You've solved for x, which was what you were looking for. X equals 2. All right, so that's finding the length of a line segment using chords that intersect inside a circle. All right, now we're going to look at tangents and secants, and this is a description, and again, many of you saw this, so if you're going over it again, then good for you, because you're absorbing more. So in the figure below, PS here, so PS is a tangent segment because it is tangent to the circle's radius. And so there's an endpoint here. This is the point of tangency. And like I said, that point is, so let's just assume this is the center of the circle. And this would be the radius. It forms a 90-degree angle here. Okay? And then the secant segment, as I said, passes, it starts on the outside, but then it goes all the way through the circle. And it has 2 endpoints there at Q and R. So the secant segment contains an external segment. So this is the external segment here. And then the whole thing is the secant, or secant segment. All right? Okay, so 2 theorems have been derived from this. One is if you have 2 secant segments, so there's 2 secant segments here, and they share the same endpoint, which they do out here at E, then the product of the length of one segment and the length of its entire segment, so in other words, if you multiply EA here times the whole thing, so the whole thing goes from here to here, and the little segment is from here to here. Okay, if you multiply this little part by the entire thing, which means you got to add together the two measurements. That's going to equal the little segment of that's from E to C, of the lower segment, or the lower tangent, times, again, the length of the entire, I said tangent, secant. So this is the E to C is the smaller segment of the lower secant, ED, and then, of course, the other part that you're multiplying it to is the entire length of the secant segment. So EA, this little part, times the whole thing, E to B, equals EC, the little part, times the whole thing of the lower secant segment, which is ED. Okay? So we're going to have to do some math for that, where we're adding together two parts to get the whole thing, and then we're multiplying that whole thing to these little parts. Okay, and one secant should equal the other secant's product. One secant's product equals the other secant's product. Okay, so that's the first one. The second one is the tangent secant rule. So if you have a secant segment and a tangent segment, then the product of the length of the secant segment and the length of its external segment, which was just what you had before. So this little part here, EC, if we multiply it to the entire thing, ED, entire secant, that should equal the square, this is the square of the length of the tangent secant. So this is going to be the squared. So we want to call this, just for the heck of it, x squared. We don't know what that value is, but it's going to be squared. Now in some problems they will give you the value for the tangent, and others they won't. But in any event, you're going to end up having to deal with a problem that includes a square, a solution that requires that you find out what x is in a quadratic equation. That's really what it comes down to. So we're going to talk about that. All right, let's move on. So here are two problems. And so this is a secant problem. And if it's a secant problem, then if you remember, we're going to multiply for secant RQ here, or yeah, RQ, we're going to multiply RP here, or let's call PR times the whole segment RQ. So times all of this. All right? And then we're going to do the same thing down here with the second secant. RS is going to be multiplied to the entire length of that SRT. Okay? So setting that up, it's going to look like this. So I've got, we'll call this PR, and it's a segment, times, now the whole thing is PR plus PQ. Okay? Because that's the whole thing. Now I can up here in the top, I could actually set it up like this. PR times, and then the whole thing is RQ. But RQ equals PR plus RQ, so you could substitute that out. All right? And then that's going to equal, and over here it's going to equal SR times RT. And RT, here's SR, I'm going to bring it down. That equals. RT is going to be RS, in parentheses, times ST. Or, I'm sorry, plus ST. Plus ST. Because we're adding them together. All right? So now let's substitute. So we're going to substitute. So when we do that, the easy part is putting in the little segments, because PR is 9 units. And we're going to multiply that times PR plus so PR is from that's the 9, right? By the way, these are line segments, so let's put the line segment symbols over everything. So PR is 9, and then R to Q is 11. So, oh, I'm sorry, P to Q. So this is P to R, this is P to Q. It looked like an R to me. So P to Q is 11 units. So we're going to add 9 plus 11. And that's going to equal SR. SR is the easy one. That's 10 units. And we're going to multiply that times RS again, plus the whole thing, which is X plus 10. So notice here, the whole thing is X plus 10, right? Just like over here, the whole thing was two things, 9 plus 11. But here you start out with 10, and X plus 10 is the second thing. Now, let me make sure I did this first one right. So 9, and then it should be 9 plus 11. Yeah. And this is X, and then it's X plus, oh, I know what I did. I did double it up. So I want to, let's just do this in red. It's X plus 10. I had an extra 10 in there. All right. So 9 times 9 plus 11. 9 plus 11 is the whole thing. And then the lower one, it's 10 plus X plus 10, or 10 plus X. Doesn't matter which way it is. It's addition. You can show it either way. All right. So now let's simplify. And so 9 plus 11, we know that's got to be 17. Oh, wait, no. 20. So this is 9 times 20 equals, and then I'm going to have to distribute here. So I'm going to distribute the 10 to the 10 and the 10 to the X. Now I could have done distribution here, but since I could simplify this way, I'm just going to distribute by now multiplying this times the total. So I'm good there. So 10 times 10 is 100. And then 10 times X is 10X. All right, we want to solve for X. So we want to undo and solve for X. We want to get the X by itself. So 9 times 20, that's 180, because 2 times 9 is 18, and then put the 0 on. And then I've got 100 plus X, plus 10X. Now I'm going to undo, so I want to subtract 100 from both sides. And I'm left with 80 over here on the left. This 100 and negative 100 cancel, and then I've got 10X. So then I divide by 10, because this is 10 times X. 10 divided by 10, of course, is 1, so I have 1X left. And 80 divided by 10 is 8. Okay. So now I know that this unknown value here is 8. And one side equals the other side. Okay? All right. Over here, I'm going to do the same thing. Now, in this case, we don't have two secants. We have a tangent in secants. Now, they didn't put letters on this. But we know that for the secant, we're going to multiply the 12 times the whole secant, which would be 12 plus 36. So I would write this, since we don't have letters, I'm just going to go ahead, except for the x, I'm going to go ahead and put the numbers in as I would think they would be. So I have x, and it's got to be squared. This value's got to be squared. So I'm going to take x and I'm going to square it. Let's use pen since we were doing pen over the other side. So x squared equals, and then 12 times 12 plus 36. Okay, so we're doing the same thing here that we were doing with each of the secants over here, as you can see. So 12 plus 36, I think that's 48. Let's just get a calculator to make sure. So clear 12 plus 36. I get 48. Okay. So x squared equals 12 times 48. Right? And then now we're going to multiply the 12 times, or the 48 times 12. So 48 times 12, and I get 576. So x squared equals 576. Now, in this situation, yes, this is a quadratic equation, but we do not have to factor it because I can take the square root of both sides. Okay? So what I'm going to do is I'm just going to use my calculator here, and I'm going to try to take the square root of 576 and see if I have a perfect square here. So I'm going to take the square root of, so I'm going to click second, and then my square root button, and then I'm going to type in 576. Okay, I get 24. So the square root of x squared equals the square root of 576. And anything squared cancels out the square root of it. And so the root is always whatever was under the radical sign over here. So this would be x. Now over here, we were actually able to take the number and find out that that number, since this isn't set up as squared under here, we use the square root and we just found out that it's 24. X equals 24. So use your calculator for these kinds of things. Now, other options. Sometimes you're left with a trinomial, x squared plus 6x plus, I don't know, 12. And you may have to then set, and that would be done by moving everything over to the right-hand side of the equation, setting the equation to 0 so that y equals 0, and then you factor. That's another way to do it, assuming that you can't do this. This is the simplest way. If that doesn't work, you may have to go to the quadratic formula. That would probably be the next go-to. There are some other intermediary steps, but I don't anticipate in this test that you're going to have a problem where you're dealing with an x squared and you have to do the quadratic formula. It'll be something more like this, or you may have to factor. Okay. All right. So this is the end of this particular lesson, and go ahead and finish the other work that you need to do. That would be the Delta Math assignments, and then do the minute quiz. Okay. All right. Take care. We'll see you later. Bye-bye now.